Hello there, and welcome to Midnight Sleep Science. Tonight, you're going to follow the journey of the most familiar substance on Earth, water. It sits in your glass right now, clear and still, yet it has traveled through billions of years in countless forms to reach you. Every molecule of water you've ever touched is older than mountains, older than forests, older than the first breath of any living thing. The same water that fills your body today once rolled across ancient oceans, froze in primordial ice, and fell as rain on landscapes you could never imagine. Water is a molecule made of just 3 atoms, 2 hydrogen, 1 oxygen, and yet it behaves unlike anything else in the universe. It expands when it freezes, clings to itself, holds heat like a vast thermal blanket, and dissolves more substances than any other liquid. This simple combination has shaped continents, carved canyons, sustained every life form that ever existed, and continues to flow quietly through your veins at this very moment. You don't just drink water. You are water, rearranged and carried forward through time. If you enjoy these gentle journeys, feel free to like and subscribe. But for now, let's begin. You begin with something so small you cannot see it, even with your naked eye. A single molecule of water. It consists of just 3 atoms, 2 hydrogen atoms bonded to 1 oxygen atom. That's all. 3 tiny pieces held together by forces you cannot feel. Yet this simple arrangement creates something extraordinary. If you could shrink yourself down to the atomic level and observe this molecule, you would notice something unusual right away. The shape is not straight, not linear, but bent. The oxygen atom sits at the center, and the 2 hydrogen atoms branch out at an angle of about 104.5 degrees. This bend is not random. It happens because of the way electrons arrange themselves around the oxygen atom, pushing the hydrogen atoms into this specific geometry. And this bend changes everything. Because of this bent shape, water becomes what scientists call polar. The oxygen atom pulls electrons toward itself more strongly than the hydrogen atoms do, creating a slight negative charge on the oxygen side and a slight positive charge on the hydrogen side. The molecule becomes electrically unbalanced, like a tiny magnet with a positive end and a negative end. This polarity is the key to almost everything water does. It's why water behaves so differently from other liquids. It's why water can dissolve salt, why it clings to glass, why it forms droplets, and why it can hold so much heat. All of this stems from the angle of a bond and the distribution of charge across 3 atoms. Now imagine billions upon billions of these bent, polar molecules together. They don't just sit next to each other. They interact. The positive hydrogen side of one molecule is attracted to the negative oxygen side of another. This attraction is called a hydrogen bond. It's not as strong as the bond holding the hydrogen and oxygen atoms together within a single molecule, but it's strong enough to matter. Hydrogen bonds form, break, and reform constantly, thousands of times per second. In liquid water, each molecule is hydrogen bonded to about 3 or 4 others at any given moment, creating a shifting, dynamic network. This network is what gives water its unusual properties, its high boiling point, its surface tension, its ability to absorb heat. Without hydrogen bonds, water would boil at -68 degrees Celsius instead of 100 degrees Celsius. It would evaporate at room temperature. There would be no liquid oceans, no rain, no rivers. Life as you know it could not exist. Let's pause here for a moment and consider what this means. Water is made of the same kinds of atoms that make up countless other molecules. Hydrogen is the most abundant element in the universe. Oxygen is produced in the hearts of dying stars. There is nothing rare about these ingredients. Yet when they come together in this specific way, bent, polar, hydrogen bonded, they create a substance that behaves unlike anything else. Water is both ordinary and exceptional. It's the most common liquid on Earth's surface, covering more than 70% of the planet. Yet it defies the rules that govern most other substances. Scientists have studied water for centuries, and they still discover new details about how it behaves under different conditions. It remains, in many ways, mysterious. One of water's most striking traits is its ability to exist in three states: solid, liquid, and gas, within the range of temperatures found naturally on Earth. Ice, liquid water, and water vapor all coexist in your environment. This is rare. Most substances exist in only one state under normal conditions. But water transitions easily between solid and liquid, between liquid and gas, because of the hydrogen bonds. When water heats up, the molecules move faster and hydrogen bonds break more frequently. When water cools, the molecules slow down and hydrogen bonds hold longer. At just the right temperature, around 0 degrees Celsius, water freezes into a solid crystal lattice, with each molecule locked into place by hydrogen bonds. At 100 degrees Celsius, water boils, and the molecules gain enough energy to break free from the liquid entirely and drift apart as vapor. These transitions happen constantly, all around you in clouds and glaciers and your breath on a cold morning. But water doesn't just transition between states. It also behaves strangely within those states. Take surface tension, for example. If you've ever seen a droplet of water beat up on a leaf or watched an insect walk across the surface of a pond, you've witnessed surface tension in action. Water molecules at the surface are hydrogen bonded to molecules beside and below them, but not above, because there's only air above. This creates an inward pull, a kind of invisible skin that holds the surface together. Surface tension is why water forms round droplets instead of spreading out into thin films. It's why you can fill a glass slightly above the rim without it spilling over. It's a direct consequence of hydrogen bonding, of water molecules clinging to each other with surprising strength. Then there's cohesion and adhesion. Cohesion is water's tendency to stick to itself, and adhesion is water's tendency to stick to other substances. Both are driven by polarity and hydrogen bonding. Cohesion is why water forms continuous columns inside the narrow vessels of plants, allowing trees to pull water from roots to leaves, sometimes hundreds of feet into the air. Adhesion is why water climbs up the sides of a glass, why it spreads across a clean surface, why it soaks into paper and fabric. Water doesn't just flow. It clings, climbs, and spreads in ways that seem almost intentional. But it's not intentional. It's chemistry. It's the result of tiny electrical attractions between molecules, repeated across trillions of interactions every second. Water also has an unusually high heat capacity, meaning it can absorb a lot of heat before its temperature rises significantly. This happens because much of the energy you add to water goes into breaking hydrogen bonds rather than increasing the speed of the molecules. Water resists temperature change. It warms slowly and cools slowly. This property has profound effects on climate, weather, and life itself, but we'll explore that more deeply later. For now, just know that water is a thermal stabilizer, a moderator of extremes. It keeps temperatures steady, both in the environment and inside your body. And finally, there's water's ability to dissolve more substances than any other liquid. This is why water is called the universal solvent. When you add salt to water, the polar water molecules surround the sodium and chloride ions, pulling them apart and holding them in solution. When you dissolve sugar, water molecules cluster around the sugar molecules, separating them from each other. Water doesn't dissolve everything. It won't dissolve oil or wax because those substances are nonpolar, but it dissolves a remarkable variety of ionic and polar compounds. This makes water an ideal transport medium. It carries nutrients through soil, minerals through rivers, oxygen through blood, and waste products out of cells. Without this dissolving power, life could not function. Cells could not exchange materials. Ecosystems could not cycle nutrients. Water is not just a passive container. It is an active participant in nearly every chemical process on Earth. So here you are, at the molecular level, understanding that everything water does, every wave, every raindrop, every river, every cell in your body, stems from this one simple bent molecule. 3 atoms arranged at an angle, creating polarity, forming hydrogen bonds, and producing a cascade of unusual behaviors. Water is not magic. It is chemistry. But the chemistry is so elegant, so perfectly suited to life and geology and climate, that it feels almost miraculous. This molecule, repeated across oceans and glaciers and clouds, has shaped the history of your planet and the story of every living thing. And now, with this understanding, you're ready to go deeper. To follow water backward through time, to the very beginning, when Earth was young and water first appeared. You step backward through time now, to an Earth that exists only in the geological record and in the evidence locked within ancient rocks. 4.5 billion years ago, the planet you call home was nothing like the place you know today. There were no oceans, no rivers, no gentle rain. Instead, there was a world of molten rock and violent impacts, a place where temperatures soared beyond what any living thing could survive. Yet somewhere in this chaos, water was waiting to be born. The water in your glass today began its story in the very materials that formed Earth itself. Scientists now believe that much of Earth's water was present from the beginning, incorporated into the rocky debris and dust that gradually came together to build the planet. This water didn't arrive later through some cosmic delivery. It was here all along, locked within the minerals and rocks that accreted to form the early Earth. Some additional water may have come from asteroids and meteorites that bombarded the young planet, but the bulk of it was likely part of Earth's original composition. But having water present and having liquid water are two very different things. During Earth's formation, the planet was essentially a ball of molten rock called a magma ocean. Temperatures reached thousands of degrees. Any water present would have been trapped within this molten mass or existed as superheated vapor in the atmosphere above. For millions of years, water existed in conditions so extreme that it couldn't settle into the familiar liquid form, The early atmosphere was a dense, hot mixture of water vapor, carbon dioxide, and other gases, all held above a surface that glowed with heat. The key moment came around 4.4 billion years ago, as Earth began to cool. The evidence for this cooling comes from tiny, nearly indestructible crystals called zircons, which formed during this ancient time and have survived to the present day. These zircons tell a remarkable story. They show chemical signatures that indicate liquid water was present on Earth's surface 4.404 billion years ago, just 200 million years after the planet formed. This is much earlier than scientists once thought possible. It suggests that as soon as the surface temperature dropped below 100 degrees Celsius, water began to condense from the vapor-laden atmosphere and fall as rain. Imagine that first rain. It may have lasted for centuries, as vast amounts of water vapor condensed out of the cooling atmosphere and poured down onto the rocky surface. This wasn't gentle precipitation. It was a deluge of epic proportions, driven by the enormous amount of water vapor that had been trapped in the hot early atmosphere. As this rain struck the cooling but still warm surface, much of it would have immediately turned back to vapor, creating an endless cycle of evaporation and condensation. But gradually, as the surface continued to cool, pools began to form. Then lakes. Then seas. The process wasn't straightforward. Early in Earth's history, there was a massive impact that created the moon, probably around 4.5 billion years ago. This impact was so violent that it likely vaporized much of Earth's crust and any water that had managed to condense on the surface. The collision threw enormous amounts of material into space and left Earth as a molten ball once again. Any oceans that had begun to form would have been destroyed, turned instantly back into vapor by the heat of impact. But water persisted. As Earth cooled again after this catastrophe, the process of condensation and ocean formation resumed. This is where the story becomes both geological and chemical. As the magma ocean slowly solidified from the bottom up, water became trapped within the crystallizing rock. But water doesn't stay trapped forever. As the interior continued to cool and solid rock formed, volcanic activity began to release this water back to the surface through a process called outgassing. Every volcanic eruption brought water vapor from deep within the Earth, adding to the water already present in the atmosphere. This created a continuous supply of water that could condense and contribute to the growing oceans. The early atmosphere was very different from today's. It contained much more carbon dioxide, which created a greenhouse effect that kept the planet warm even as it was cooling from its molten state. This was crucial for keeping water in liquid form during a time when the sun was actually about 30% dimmer than it is today. Without this greenhouse effect, Earth might have frozen solid, and all the water would have turned to ice. Instead, the combination of atmospheric composition and planetary heat created conditions where liquid water could exist and accumulate. By around 3.8 billion years ago, there is clear geological evidence that liquid water oceans existed on Earth's surface. This evidence comes from pillow basalts, rocks that form only when lava erupts underwater, found in ancient formations like the Isua Greenstone Belt. These rocks are unmistakable proof that liquid water, enough to allow underwater volcanic eruptions, was present nearly 4 billion years ago. The oceans had formed. But these early oceans were unlike anything you would recognize today. They were likely much hotter, perhaps reaching temperatures of 70 to 80 degrees Celsius in some regions. They were also more acidic and contained different dissolved minerals than modern seawater. The water itself was the same H2O molecule, with the same bent shape and polar properties, but the environment was alien. There was little or no oxygen in the atmosphere, and the oceans teemed with chemical reactions that would eventually give rise to life. What's remarkable is that this process, the formation of stable liquid water ocean, happened relatively quickly in geological terms. Within about 700 million years of Earth's formation, liquid water had gone from non-existent to abundant. The same molecules that started as vapor in a hellish early atmosphere had cooled, condensed, and settled into the basins and low-lying areas of the cooling planet. Gravity held them there, creating the first reservoirs of liquid water that would remain stable for billions of years to come. This early water was the beginning of everything that would follow. It was the medium in which the first complex chemical reactions occurred, the environment where the first life appeared, and the foundation of the water cycle that would reshape the planet's surface for billions of years. The water molecules in your glass today are direct descendants of those first drops that fell from the cooling sky of a young Earth. They have been cycling through the same processes ever since, evaporating, condensing, flowing, and maintaining the conditions that make life possible. From fire and vapor, from heat and time, from the gradual cooling of a molten world, your water was born. Now you need to understand what that first ocean actually looked like, because it was not the blue expanse you imagine when you think of water today. Around 3.8 billion years ago, when the primeval ocean had finally settled into the basins of the cooling Earth, you would have encountered a world almost unrecognizable. The water itself was chemically the same, still H2O, still polar, still hydrogen bonded, but everything about its environment was different. The temperature of this early ocean was much higher than modern seawater. Some scientists estimate that surface temperatures could have reached 70 to 80 degrees Celsius, hot enough to make swimming impossible, hot enough to kill most organisms that exist today. In some regions, particularly near underwater volcanic vents, temperatures would have been even higher. The ocean was hot because Earth itself was still cooling from its formation, and because the atmosphere contained far more greenhouse gases, primarily carbon dioxide, than it does now. This thick carbon dioxide-rich atmosphere trapped heat like an insulating blanket, keeping the surface warm even though the young sun was about 30% dimmer than it is today. The color of the ocean may have been different too. Instead of the familiar blue, the early ocean might have appeared greenish due to high concentrations of dissolved iron. This iron came from volcanic activity and from the weathering of the newly forming crust. Ferrous iron, which is soluble in water, could exist in large quantities in the oxygen-poor environment of the early ocean. There was virtually no free oxygen in the atmosphere or dissolved in the water at this time. The chemistry was fundamentally different from what you know today. The ocean was also likely more acidic than modern seawater. The high concentration of carbon dioxide in the atmosphere dissolved readily into the water, forming carbonic acid and lowering the pH. This acidic water reacted aggressively with the rocks it contacted, dissolving minerals and creating a soup of dissolved chemicals that will become crucial for the development of life. The water was salty, though perhaps not with exactly the same salts in the same proportions as today. Sodium, chloride, magnesium, calcium, and other ions accumulated as the water weathered the surrounding rocks and received chemical input from volcanic gases. The physical extent of this ocean is a matter of ongoing scientific debate. Some evidence suggests there may have been a single vast ocean covering most of the planet's surface. Other evidence indicates there may have been multiple separate bodies of water, with land masses and volcanic islands scattered throughout. What is certain is that liquid water was present, stable, and accumulating in the low-lying areas of Earth's surface. Gravity held it there, preventing it from escaping into space. The water had found its home. This early ocean was not a static, lifeless pool. It was chemically active, constantly reacting with the rocks beneath it, with the atmosphere above it, and with the volcanic gases bubbling up from the Earth's interior. Hydrothermal vents on the ocean floor release superheated water rich in minerals and chemical compounds. These vents created localized environments with extreme temperature gradients and unusual chemistry, zones where hot mineral-rich water met cooler seawater. These environments would later prove crucial for the emergence of life, but even before life appeared, they drove chemical reactions that made the ocean increasingly complex. The ocean also played a critical role in shaping Earth's climate and geology during this period. Water has an enormous capacity to absorb and store heat. The vast body of water covering much of the planet acted as a thermal buffer, absorbing heat during the day and releasing it slowly at night, moderating temperature extremes. Water also participated in the carbon cycle, dissolving carbon dioxide from the atmosphere and eventually helping to precipitate it as carbonate minerals on the seafloor. This process gradually reduced the amount of greenhouse gases in the atmosphere, allowing the planet to cool further over millions of years. Evidence of this ancient ocean comes from multiple sources. The pillow basalts found in the Isua Greenstone Belt in Greenland are perhaps the most direct evidence. These rocks form only when lava erupts underwater and cools rapidly, creating characteristic pillow-shaped structures. The presence of these structures in 3.8 billion-year-old rocks proves that there was enough liquid water at that time to allow submarine volcanic eruptions. Other evidence comes from ancient sedimentary rocks, which form only in the presence of liquid water, and from chemical signatures and minerals that indicate they crystallized in a water-rich environment. By 3.5 billion years ago, just 300 million years after the ocean formed, there is evidence of life in the form of stromatolites, layered structures created by communities of microorganisms. The fact that life appeared so quickly after the ocean stabilized suggests that the conditions in that early ocean, despite being hot and chemically strange by modern standards, were suitable for the chemistry of life to emerge. The water provided a medium for chemical reactions, a solvent for transporting nutrients and minerals, and a stable environment protected from the harsh radiation and temperature extremes of the surface. The first ocean was not the destination, but the beginning. Over the next billion years, the ocean would continue to evolve. Oxygen would gradually accumulate, first from the activity of photosynthetic organisms and later from the breakdown of water molecules in the upper atmosphere. The chemistry would shift as minerals precipitated out of solution, and as volcanic activity gradually declined. The temperature would slowly drop as greenhouse gases were sequestered and the planet continued to cool. By about 2 billion years ago, the ocean had achieved chemical characteristics remarkably similar to the modern ocean. But that process took over 1 billion years of continuous evolution. Standing at the edge of that first ocean, you would have felt the same water that flows through rivers today, the same water that fills your glass. The molecules were identical, but the context was alien, hot, acidic, greenish, bubbling with volcanic gases under a thick atmosphere that blocked much of the sunlight. Yet this was the crucible in which life would emerge, the environment. That would give rise to the first cells, the first metabolisms, the first reproduction. The ocean had formed, and with it, the stage was set for everything that would follow. The ocean had formed, but it didn't simply sit still. From the moment the first raindrops fell and pooled in the ancient basins, water began a process that has never stopped, a continuous cycle of movement, transformation, and return. This is the water cycle, and it has been running for nearly 4 billion years. Every molecule of water in your glass has passed through this cycle countless times, moving from ocean to sky to land and back again in an endless loop driven by two fundamental forces: the energy of the sun and the pull of gravity. The process begins with evaporation. The sun's energy strikes the surface of the ocean, lakes, rivers, and soil, and that energy breaks the hydrogen bonds holding water molecules together in liquid form. Individual molecules gain enough kinetic energy to escape into the air as water vapor. This happens constantly, everywhere there is water and sunlight. The ocean is a primary source, releasing enormous quantities of water vapor into the atmosphere every day. About 86% of global evaporation comes from the oceans. But evaporation also occurs from lakes, rivers, soil, and even from the surfaces of plants through a process called transpiration. Plants draw water up from the soil through their roots and release it through tiny pores in their leaves. This plant-driven evaporation adds significantly to the total amount of water entering the atmosphere. Once in the atmosphere, water vapor rises. Warm air, which can hold more water vapor than cold air, carries the moisture upward. As the air rises, it expands and cools. Eventually, it reaches a temperature where it can no longer hold all its water vapor. The air becomes saturated. At this point, condensation begins. Water vapor molecules slow down, hydrogen bonds reform, and the vapor transitions back into tiny liquid droplets. These droplets are incredibly small, often just micrometers in diameter. They cluster around microscopic particles in the air, dust, salt crystals, pollen, or pollution, which serve as condensation nuclei. Billions of these tiny droplets gather together, and they become visible as clouds. Clouds are not permanent structures. They are constantly forming, shifting, and dissipating as air currents move them through regions of different temperature and humidity. Within a cloud, droplets collide and merge, growing larger. When they become heavy enough, gravity takes over. The droplets fall as precipitation, rain, if the air is warm enough, or snow, sleet, or hail if temperatures are below freezing. Precipitation returns water from the atmosphere to the Earth's surface. About 77% of precipitation falls directly back into the ocean, where it came from. The remaining 23% falls on land. When precipitation reaches land, several things can happen. Some water soaks into the soil through a process called infiltration. This water may be absorbed by plant roots, used by organisms in the soil, or percolate deeper to recharge underground aquifers. Aquifers are layers of porous rock or sediment that hold water beneath the surface, sometimes for thousands of years. Water stored underground moves slowly through these formations and may eventually emerge at springs or seep into rivers and lakes. Some precipitation lands on surfaces that don't absorb water well: rock, pavement, saturated soil, and this water flows across the surface as runoff. Runoff collects in streams, which join to form rivers, which eventually flow back to the ocean. The journey from mountaintop to sea can take days, weeks, or months, but gravity ensures that surface water always moves downhill. Throughout this journey, water continues to evaporate. A river flowing through a warm valley releases water vapor into the air. A lake in summer loses more water to evaporation than it receives from rainfall. Even snow and ice can transition directly from solid to vapor through sublimation, skipping the liquid phase entirely. All of this water vapor enters the atmosphere, rises, cools, condenses, and eventually falls again as precipitation. The cycle is continuous, self-sustaining, and powered entirely by solar energy and gravity. This cycle has been operating since shortly after the ocean formed. Evidence from ancient rocks shows that water was cycling between land and sea at least 3.5 billion years ago. The presence of sedimentary rocks, formed from particles eroded and transported by water, proves that rivers were flowing. The existence of weathered minerals indicates that rain was falling on land and chemically reacting with rocks. The water cycle shaped the early Earth just as it shapes the planet today. It eroded newly formed continents, carved valleys, deposited sediments, and transported dissolved minerals from land to ocean. The water cycle is also a heat redistribution system. When water evaporates, it absorbs a large amount of heat energy, the heat of vaporization. This energy is carried upward with a water vapor into the atmosphere. When the vapor condenses back into liquid, that stored heat is released. This process transfers enormous amounts of energy from Earth's surface, particularly from the tropical oceans, into the atmosphere where it drives weather patterns and ocean currents. Without the water cycle, Earth's climate would be far more extreme, with greater temperature differences between equator and poles, between day and night, between summer and winter. The cycle operates on vastly different timescales depending on where water resides. Water in the atmosphere has a residence time of only about 9 days on average. It evaporates, forms clouds, and falls as precipitation relatively quickly. Water in rivers moves faster still, typically reaching the ocean within weeks or months. Water in the ocean has a much longer residence time, around 3,000 years on average, because the ocean is so vast and evaporation affects only the surface. Water locked in glaciers and ice sheets can remain frozen for tens of thousands or even hundreds of thousands of years before melting and rejoining the active cycle. Water in deep aquifers may reside underground for millennia. Yet all of this water is part of the same system, the same continuous circulation. The total amount of water on Earth has remained relatively constant for billions of years. The cycle doesn't create new water or destroy old water. It simply moves the same water through different states and locations. The water in your glass has been through this cycle countless times. Some of its molecules may have fallen as rain on Precambrian mountains, flowed through rivers that no longer exist, evaporated from ancient oceans, and returned to Earth long before complex life appeared. Other molecules may have been locked in polar ice for millennia before melting and entering a river just decades ago. The water cycle connects all times and all places where water exists. It is both immediate and eternal, constantly moving yet fundamentally unchanged for billions of years. You journey back now, deeper into time, to an Earth that existed only in the violent beginning. 4.5 billion years ago, there were no oceans yet, no continents, no familiar landscapes. The planet was newly formed from the collision and accretion of countless rocks and debris orbiting the young sun. What you would have witnessed, if you could somehow observe from a safe distance, was a molten sphere, a ball of liquid rock glowing with heat from the energy of impacts and from the decay of radioactive elements deep in its core. The surface temperature was measured in thousands of degrees. Nothing solid existed. This was Earth during what scientists call the Hadean Eon, named after Hades, the ancient underworld, because conditions were so hellish. At this early stage, Earth had almost no atmosphere to speak of. Any gases that had been part of the original material from which the planet formed, primarily hydrogen and helium from the solar nebula, were stripped away by the intense heat and by radiation from the young sun. These lightest gases simply escaped into space. What remained was a nearly airless rock, its surface a churning ocean of magma, with temperatures so extreme that even metal vaporized. Yet water was there, hidden within this inferno. It existed not as liquid, not even as vapor floating free, but locked within the minerals and rocks that had come together to build the planet. The water had come from multiple sources. Much of it was incorporated into the planetesimals, the building blocks of planets that collided and merged to form Earth. These rocky bodies contained water bound chemically within minerals, carried inward from the cooler outer regions of the solar system where water ice was stable. When these planetesimals collided with a growing Earth, their water became part of the planet's composition. Additional water may have arrived later through impacts from asteroids and comets during a period of heavy bombardment. Comets, which are essentially dirty snowballs composed largely of ice, brought water directly to Earth's surface when they struck. Each impact delivered more of this essential molecule, gradually building up the planet's total water inventory. But having water present and having it in a form you would recognize are entirely different matters. During the Hadean, with surface temperatures far above the boiling point, any water that reached the surface immediately vaporized. The intense heat from impacts, from the gradual settling and differentiation of Earth's layers, and from radioactive decay kept the entire planet molten. Water existed as superheated steam mixed with other volcanic gases in a thick, dense atmosphere above the magma ocean. This early atmosphere was nothing like the air you breathe today. It contained enormous quantities of water vapor, carbon dioxide, nitrogen, and smaller amounts of methane, ammonia, hydrogen sulfide, and other gases released from the molten interior. There was virtually no free oxygen. The atmosphere was thick, heavy, and opaque, more like the crushing atmosphere of Venus than the breathable air of modern Earth. This hellish phase could not last forever. Gradually, over millions of years, Earth began to cool. The frequency of large impacts decreased as the solar system cleaned itself of debris. The heat from radioactive decay, while still substantial, was no longer enough by itself to keep the entire surface molten. The magma ocean began to solidify from the bottom up as minerals crystallized and sank, forming the first solid crust. This cooling was slow but inexorable. As the surface temperature dropped, a critical threshold was eventually crossed. The temperature fell below the boiling point of water. When this happened, something extraordinary occurred. The water vapor that had been trapped in the hot atmosphere began to condense. Hydrogen bonds formed between the cooling water molecules, pulling them together into liquid droplets. These droplets grew heavy and fell as rain. It must have been a rain unlike anything you've ever experienced, a torrential, unceasing deluge that may have lasted for thousands or even hundreds of thousands of years. The entire water content of the atmosphere, built up over millions of years of volcanic outgassing and comet impacts, came pouring down onto the still hot surface. At first, the rain didn't accumulate. The surface was still too hot. Raindrops striking the rocks vaporized instantly, turning back into steam and rising into the atmosphere only to cool and fall again. This cycle repeated endlessly, rain falling, evaporating on contact, rising, condensing, falling again. But as the surface continued to cool, more and more of the water remained liquid. Puddles formed, then pools, then lakes. Water began to collect in the low-lying areas, the basins and depressions in the newly solidified crust. Gravity held the water in these basins, preventing it from escaping back into space. Slowly, relentlessly, the first bodies of standing water appeared on Earth's surface. The timeline of this cooling and condensation has been reconstructed through careful study of ancient rocks. The key evidence comes from zircon crystals, tiny, nearly indestructible minerals that form in molten rock and survive for billions of years. Zircons from Western Australia, some of the oldest materials ever found on Earth, date back to about 4.4 billion years ago. Chemical analysis of these zircons reveals something remarkable. They contain oxygen isotope ratios that indicate they formed in the presence of liquid water. This means that just 160 million years after Earth formed, and less than 100 million years after the moon-forming impact that would have remelted the surface, liquid water had already appeared. The planet cooled faster than scientists once thought possible. This early water was not yet a global ocean. It existed as scattered seas and lakes dotting a landscape of volcanic rock. The atmosphere was still thick with carbon dioxide, creating a powerful greenhouse effect that kept temperatures warm despite the young sun being about 30% dimmer than it is today. This greenhouse effect was essential. Without it, Earth would have frozen solid, and all the water would have turned to ice. Instead, the balance was just right, warm enough for liquid water to remain stable on the surface, cool enough for that water to accumulate rather than evaporate immediately. The process of water accumulation continued through volcanic outgassing. Volcanoes weren't just occasional events in the early Earth. They were constant and widespread. Each eruption released more water vapor from deep within the planet, where it had been trapped in minerals since Earth's formation. This water rose through the crust as magma pushed toward the surface, then escaped into the atmosphere as steam when the magma erupted. Over millions of years, this continuous outgassing transferred enormous quantities of water from Earth's interior to its surface. The oceans were being filled not just by the primordial rain, but by an ongoing supply of new water emerging from below. By about 3.8 billion years ago, This process had created something recognizable, a true ocean, or perhaps multiple oceans, covering significant portions of Earth's surface. The evidence for this comes from multiple sources: pillow basalts that form only underwater, sedimentary rocks that require liquid water to deposit, and chemical signatures in ancient minerals that indicate they interacted with seawater. Water had made the transition from trapped mineral component to superheated vapor to falling rain to standing liquid to stable ocean. Born in the fire of Earth's formation, tempered by the ice-cold void of space from which its ingredients came, water had finally found its home on the planet's surface. The primordial ocean, once formed, didn't remain static. During the late Hadean and early Archean eons, between about 4 billion and 3 billion years ago, Earth's water distribution looked dramatically different from what you see today. Recent geochemical calculations and geological evidence suggest that Earth may have been what scientists now call a water world, a planet where the ocean was significantly larger than it is today, possibly covering almost the entire surface. The reason for this lies in the competing processes that shaped early Earth. On one hand, the ocean was growing as volcanic outgassing continued to release water from the planet's interior. The mantle during the Hadean contained substantially more water than it does today, perhaps several times as much. As magma rose and crystallized, this water was gradually expelled to the surface through continuous volcanic activity. By the end of the Hadean, the mantle had lost most of its water to form what some researchers describe as a deep surface ocean. On the other hand, continental crust, the less dense rock that forms land masses, was only beginning to develop. The processes that create continents, including partial melting of the mantle and differentiation of lighter minerals, operated differently in the hotter early Earth. The result was an imbalance. Recent research suggests that over very long timescales, billions of years, more water may be entering the mantle through subduction than is being released through volcanism, meaning Earth's surface may be slowly drying out. But these changes occur on geological timescales and don't affect the fundamental operation of the cycle. The water in your glass has passed through this cycle countless times. Some of its molecules may have fallen as rain on ancient landscapes that no longer exist, flowed through rivers that have long since disappeared, and evaporated from seas that dried up millions of years ago. Other molecules may have been locked in Antarctic ice for 100,000 years before melting just decades ago and entering a river that eventually flows from your tap. The cycle connects all times and all places where water exists. It has been running continuously day and night, through ice ages and warm periods, through mass extinctions and evolutionary radiations, for nearly 4 billion years. The water cycle doesn't just move water, it shapes Earth itself. Over geological time, water has been the single most powerful sculptor of the planet's surface, carving valleys, building deltas, weathering mountains, and transforming solid rock into sediment that travels from highlands to ocean basins. This process has been operating since the early Archean, at least 3.5 billion years ago, when there was enough continental land above sea level to experience rainfall and erosion. The evidence is written in ancient sedimentary rocks, layers of sand, silt, and clay that could only form through the action of flowing water. The cycle works through a mechanism called the rock cycle, which is intimately connected to the water cycle. Rain falls on exposed rock and begins chemical weathering. Acids in rainwater, particularly carbonic acid formed when carbon dioxide dissolves in water, react with minerals in the rock. Feldspars, which make up a large fraction of many rocks, are broken down into clay minerals. Silica is dissolved and carried away in solution. Metals like iron, calcium, and magnesium are extracted from crystal structures and enter water as dissolved ions. This chemical weathering, combined with physical weathering from freeze-thaw cycles, plant roots, and mechanical abrasion, gradually breaks solid rock into smaller particles. Once rock has been broken down into particles, water transports them. Rain falling on slopes creates runoff that carries fine particles of clay and silt. Streams and rivers transport larger particles, sand and gravel, rolling them along the riverbed or carrying them suspended in the current. The capacity of a river to transport sediment depends on its velocity. Fast-moving water in steep mountain streams can move surprisingly large boulders, while slow-moving water in flat plains can only carry fine silt. Over millions of years, rivers transport enormous quantities of sediment from eroding highlands to lowland basins and eventually to the ocean. When rivers reach the ocean or flow into lakes, their velocity decreases and they lose their ability to carry sediment. The sediment settles out in order of size: coarse gravel and sand near the river mouth, finer silt and clay farther out. This creates distinctive fan-shaped deposits called deltas, which build outward into the water body over time. The Mississippi River Delta, the Nile Delta, the Ganges Delta. All of these are built from sediment eroded from continental interiors and transported by rivers to the sea. These deltas can be hundreds of kilometers across and thousands of meters thick, representing millions of years of continuous sediment delivery. Sediment deposited on the ocean floor or in lake basins doesn't just sit there indefinitely. As more sediment accumulates on top, the weight compresses the lower layers. Water is squeezed out from between the grains. Minerals dissolve in the water precipitate and cement the grains together, transforming loose sediment into solid sedimentary rock: sandstone, shale, limestone. This process, called lithification, typically takes millions of years and occurs at depths of hundreds to thousands of meters below the seafloor. But the story doesn't end there. Earth's surface is dynamic, driven by plate tectonics, the movement of large sections of Earth's lithosphere across the planet's surface. Plate tectonics may have begun operating in some form as early as 3.8 billion years ago, though the modern style of plate tectonics probably didn't become fully established until much later, possibly around 800 million to 2 billion years ago, depending on how you define it. Regardless of exactly when it started, plate tectonics has played a crucial role in recycling Earth's surface materials, including water. In subduction zones, where one tectonic plate descends beneath another, sediment deposited on the ocean floor is carried downward into the Earth's interior. Some of this sediment is scraped off and added to the overlying plate, building mountain ranges along continental margins. But some continues downward, carrying water-bearing minerals deep into the mantle. The water in these minerals is released as the rocks heat up, rising back toward the surface where it emerges through volcanic eruptions. This deep water cycle operates on timescales of tens to hundreds of millions of years. Meanwhile, in collision zones where two continental plates meet, sedimentary rocks that formed on ancient seafloors are compressed, folded, and uplifted to form mountain ranges. The Himalayas, the Alps, the Appalachians, all of these were built partly from sediments that accumulated underwater and were then thrust upward by tectonic forces. Once these rocks are lifted above sea level, they become subject to erosion again. Rain falls on the newly formed mountains, streams cut into the rock, and the cycle of weathering, transport, and deposition begins anew. This has been happening continuously for billions of years. Mountains rise through tectonic forces, water erodes them, sediment is transported to the ocean, new rocks form, and then tectonics lifts those rocks back above sea level to be eroded again. The process is slow. It takes millions of years to build a mountain range and millions more to erode it away, but it's relentless. Every mountain range on Earth today is being worn down by water. Every beach is being built from sediment eroded from somewhere upstream. Every delta is growing outward, carrying material from continental interiors to the sea. The power of water to reshape landscapes is most visible in dramatic features like canyons. The Grand Canyon, carved by the Colorado River over millions of years, exposes rock layers that record 1.8 billion years of Earth history. Each layer was deposited as sediment, lithified into rock, then cut through by the river as it carved downward. The canyon is more than 400 kilometers long and in places more than 1,800 meters deep, all carved by flowing water carrying abrasive sediment. You followed water through its cycle from ocean to atmosphere and back, and now you need to see what that cycle accomplishes over geological time. Water doesn't just flow across Earth's surface, it fundamentally transforms it. Over billions of years, water has carved valleys, built plains, weathered mountains into sand, and reshaped every landscape you see today. This sculpting process operates continuously, patiently, with a power that becomes apparent only when viewed across millions of years. The transformation begins the moment rainwater touches rock. Rain is not pure water. It contains dissolved carbon dioxide from the atmosphere, which makes it slightly acidic. This weak carbonic acid reacts with minerals in the rock. Feldspars, which make up about 60% of Earth's continental crust, slowly decompose when exposed to acidic water. The chemical bonds holding the crystal structure together break apart, and the feldspar transforms into clay minerals while releasing dissolved ions, sodium, potassium, calcium, into the water. Silica dissolves and is carried away in solution. Even seemingly inert minerals like quartz eventually weather, though far more slowly than feldspars. This chemical weathering happens everywhere water contacts rock, but it's most effective in warm, humid climates where there's abundant rainfall and where higher temperatures speed up chemical reactions. In tropical regions, chemical weathering can penetrate tens of meters below the surface over millions of years, transforming solid bedrock into thick layers of clay-rich soil. In cold, dry climates, chemical weathering proceeds much more slowly, and physical weathering, the mechanical breaking of rock without changing its chemistry, becomes more important. Physical weathering operates through several mechanisms. Water seeps into cracks in rock, and when temperatures drop below freezing, the water turns to ice. Ice occupies about 9% more volume than liquid water, one of water's anomalous properties stemming from the geometry of hydrogen bonds in the ice crystal structure. This expansion exerts tremendous force on the surrounding rock, wedging the crack open wider. When the ice melts, water penetrates deeper into the widened crack, and the cycle repeats. Over thousands of freeze-thaw cycles, this process can split massive boulders and break apart cliff faces. Plant roots also contribute to physical weathering. As roots grow, they follow cracks in rock, and their expanding growth forces the cracks wider. When you see a tree growing from a crack in a boulder, you're witnessing physical weathering in action. On a larger scale, entire forests contribute to weathering by creating organic acids in the soil that enhance chemical breakdown of minerals. Once rock has been broken down into smaller particles, whether through chemical transformation into clay or physical fragmentation into sand and gravel, water becomes the primary transport agent. When rain falls on a slope, it doesn't immediately soak into the ground if the rain is falling faster than the soil can absorb it. Instead, water flows across the surface as a thin sheet, and this sheet flow has just enough energy to pick up and carry fine particles of clay and silt. As the water moves downslope, it concentrates into small channels called rills. Rills merge to form larger channels called gullies, and gullies feed into streams. Streams have more power than sheet flow, because water concentrated in a channel moves faster and can carry larger particles. The capacity of flowing water to transport sediment depends on its velocity. Double the velocity, and the water can carry particles that are 64 times heavier. Fast-moving mountain streams in steep terrain can roll boulders weighing hundreds of kilograms along their beds during floods. The boulders tumble and collide with each other, and with the bedrock channel, gradually becoming smaller and more rounded. Sharp corners break off, angular rocks become rounded cobbles. Cobbles become gravel, gravel becomes sand. As streams flow from steep mountains into gentler terrain, their velocity decreases and they lose the ability to carry the largest particles. Boulders and cobbles are left behind in the upper reaches, while finer sand, silt, and clay continue downstream. This sorting of sediment by size creates characteristic patterns: coarse material near the headwaters, increasingly fine material downstream. When multiple streams join to form a river, the combined flow can transport enormous quantities of sediment. The Amazon River, the largest river on Earth by discharge, carries about 1.1 billion tons of sediment to the ocean every year. The Ganges-Brahmaputra system carries even more, about 1.6 billion tons annually. Rivers don't just transport sediment, they also carve the landscape through which they flow. The mechanism is called fluvial erosion. Sediment particles carried by the river act as abrasives, scouring the riverbed and banks. Over time, rivers cut downward into bedrock, creating V-shaped valleys in mountainous terrain. The rate of downcutting depends on Several factors: the river's discharge, the amount and hardness of sediment it carries, and the resistance of the bedrock. Rivers flowing through soft sedimentary rocks cut down quickly. Rivers flowing through hard crystalline rocks cut much more slowly. The Grand Canyon represents perhaps the most dramatic example of river erosion. The Colorado River has been cutting downward through layers of sedimentary rock for about 5 to 6 million years, carving a gorge more than 1,800 meters deep in places. The river exposes rock layers spanning 1.8 billion years of Earth history. Each layer tells a story: ancient seas that deposited limestone, deserts that left sandstone, rivers that laid down shale. All of these rocks, which formed through earlier cycles of erosion and deposition, are now being eroded again as the Colorado River cuts through them. Rivers don't flow in straight lines. They develop meanders, sinuous curves that swing back and forth across the valley floor. Meanders form because water flowing around even a slight bend moves faster on the outside of the curve than on the inside. The faster-moving water on the outside erodes the bank, while slower-moving water on the inside deposits sediment. This differential erosion and deposition causes the meander to gradually migrate sideways across the valley. Over centuries, meanders can shift position by hundreds of meters. Sometimes the meander loop becomes so extreme that the river cuts through the narrow neck of land, abandoning the loop and creating an oxbow lake. When rivers finally reach the ocean, their velocity drops dramatically and they lose their capacity to carry sediment. The sediment that the river has been transporting, sometimes for thousands of kilometers, settles out of the water and accumulates on the ocean floor. This deposition follows a predictable pattern based on particle size and weight. The heaviest particles, like gravel and coarse sand, settle out first, close to where the river enters the ocean. Finer sand settles farther out. Silt settles in even deeper, calmer water. The finest clay particles can remain suspended for long distances before finally settling in the quietest, deepest parts of the ocean basin. This process builds deltas, fan-shaped deposits of sediment that extend outward from river mouths into the ocean or into lakes. Deltas can be enormous. The Ganges-Brahmaputra Delta in Bangladesh covers more than 100,000 square kilometers. The Mississippi River Delta has been building for thousands of years, constantly extending Louisiana's coastline into the Gulf of Mexico. These deltas represent the end point of continental erosion, material that was once part of mountain ranges hundreds or thousands of kilometers upstream, weathered into particles, transported by rivers, and finally deposited at the river mouth. But the sediment doesn't just pile up indefinitely as loose grains. As more sediment accumulates on top, the weight of the overlying material compresses the layers below. This process is called compaction. Water that was originally present between the sediment grains is squeezed out. The grains are pressed closer together, reducing the pore space. If the sediment contains soft materials like clay or fragments of organic matter, they flatten under the pressure. Simultaneously, cementation occurs. Water percolating through the sediment carries dissolved minerals, typically calcite, silica, or iron oxides. These minerals precipitate out of solution in the pore spaces between sediment grains, forming a natural cement that binds the grains together. You've probably seen this process in miniature on old plumbing fixtures, where dissolved calcium carbonate precipitates from hard water and forms crusty deposits. The same chemical process, operating over millions of years in sedimentary deposits, transforms loose sediment into solid rock. The combination of compaction and cementation is called lithification, literally rock making. Through lithification, layers of sand become sandstone, layers of silt become siltstone, and layers of clay become shale. The process typically requires burial depths of hundreds to thousands of meters and timescales of millions of years. Temperature and pressure increase with depth, accelerating the chemical reactions that cement grains together. The resulting sedimentary rock preserves the layered structure of the original sediment deposits, with each layer representing a distinct period of deposition. These sedimentary layers record Earth's history. Each layer contains information about the environment in which it formed, the climate, the water depth, the types of organisms present. Fossils preserved in sedimentary rocks provide a record of life's evolution over hundreds of millions of years. The Grand Canyon's layered walls are sedimentary rocks spanning 1.8 billion years, each layer telling a story of ancient seas, rivers, and deserts. But the cycle doesn't end with lithification. Plate tectonics ensures that sedimentary rocks don't remain buried on the ocean floor forever. In subduction zones, where one tectonic plate descends beneath another, some oceanic sediments are scraped off and accreted onto the edge of the overriding plate. This process builds mountain ranges along continental margins. The Andes Mountains, for example, are partly composed of sediments that accumulated on the ocean floor, were scraped off the descending oceanic plate, and were thrust upward into mountains. In collision zones, where two continental plates meet, sedimentary rocks deposited in ancient ocean basins are compressed, folded, and uplifted. The Himalayas contain limestone formed from the shells of marine organisms that live in a shallow sea called the Tethys Ocean. When the Indian subcontinent collided with Asia about 50 million years ago, the seafloor was crumpled and lifted, eventually forming the highest mountains on Earth. Marine fossils now sit at elevations above 8,000 meters, carried there by tectonic forces. Once sedimentary rocks are lifted above sea level through tectonic uplift, they become subject to erosion again. The water cycle resumes its work. Rain falls on the newly exposed rocks. Chemical weathering breaks down the minerals. Physical weathering fragments the rocks, and rivers transport the resulting sediment back toward the ocean. The same material may go through this cycle multiple times over hundreds of millions of years, deposited as sediment, lithified into rock, uplifted into mountains, eroded back into sediment, and deposited again. This is the rock cycle, and water drives it at every step. Water weathers rock through chemical reactions. Water transports the weathering products as rivers carry sediment. Water provides the medium in which sediments are deposited and sorted. Water carries the dissolved minerals that cement sediments into rock. And water, through its role in plate tectonics, lubricating subduction zones and affecting the viscosity of the mantle, helps drive the tectonic forces that uplift rocks and restart the cycle. Over billions of years, water has recycled Earth's crust countless times. Every mountain range currently on Earth is the product of this cycle, and every mountain range is being actively dismantled by it. The Appalachian Mountains in eastern North America, which formed about 480 to 300 million years ago, were once as high as the Himalayas. Water has been eroding them ever since, carrying their substance grain by grain to the Atlantic Ocean. In a few hundred million years, the Himalayas will suffer the same fate, worn down by water into gentle hills. And somewhere else new. Mountains will rise from sediments that the Himalayas provided, continuing the endless cycle of transformation. You followed water through its cycle and watched it reshape continents, but now you need to understand one of water's strangest and most consequential properties: what happens when it freezes. This behavior is so unusual, so contrary to how almost every other substance works, that if water behaved normally, life as you know it could not exist. When most liquids freeze, they become denser. The molecules pack more closely together in the solid state than they did in the liquid state. This makes intuitive sense. Solids are more organized and compact than liquids, so they should take up less space. And indeed, this is how nearly every substance behaves. When molten rock solidifies, it contracts. When liquid wax cools into solid wax, it shrinks. When metals freeze from molten to solid, they become denser and sink. Water does the opposite. When water freezes into ice, it becomes less dense. Ice floats on liquid water. This is so familiar that you might not recognize how strange it is, but it represents a fundamental anomaly in the physical behavior of matter. The reason lies in the molecular structure of water and the geometry of hydrogen bonds. In liquid water, molecules are constantly moving, forming and breaking hydrogen bonds with their neighbors thousands of times per second. Each molecule is hydrogen bonded to an average of about 3 or 4 others at any given moment, but the arrangement is dynamic and irregular. The molecules pack together fairly efficiently, with hydrogen bonds holding them at various angles. As temperature drops and molecules slow down, more hydrogen bonds form and persist for longer periods. When water cools below 0 degrees Celsius, the molecules slow down enough that hydrogen bonds can hold them in fixed positions. But the hydrogen bonds don't allow the molecules to pack together in just any arrangement. The bent shape of the water molecule and the geometry of hydrogen bonding dictate a specific structure. Each water molecule in ice forms hydrogen bonds with exactly 4 neighbors, arranged in a tetrahedral pattern, 1 neighbor above, 1 below, and 2 on the sides. This creates a hexagonal crystal lattice with lots of empty space between the molecules. This hexagonal structure is what you see when you look at a snowflake. The six-fold symmetry of snowflakes reflects the six-fold symmetry of the ice crystal structure. Every snowflake, despite its unique detailed pattern, has this basic hexagonal symmetry because that's the only way water molecules can arrange themselves when they freeze. The intricate patterns form as the growing ice crystal encounters slightly different conditions of temperature and humidity as it falls through the atmosphere, but the underlying six-sided structure is always present. The crucial point is that this hexagonal arrangement is less efficient at packing molecules together than the irregular arrangement in liquid water. Ice has more empty space between molecules than liquid water does. This means ice occupies about 9% more volume than the same mass of liquid water. This is why ice is less dense than water and why it floats. You can observe this every time you freeze water in a container. The ice expands, sometimes cracking the container if it's rigid. This expansion exerts tremendous force, enough to split rocks through frost wedging, as you've already seen, enough to burst water pipes in winter. The force comes not from any external pressure, but simply from the geometric requirements of hydrogen bonding in the ice crystal structure. The fact that ice floats has profound consequences for life on Earth. When winter comes to a lake or pond, the surface water cools first because it's in direct contact with cold air. As this water cools below 4 degrees Celsius, water's temperature of maximum density, it becomes lighter and stays at the surface. When it freezes, the ice remains on top, forming a layer that insulates the water below. This insulating ice layer is critical. It prevents the cold air from directly contacting the liquid water beneath. The water below the ice remains liquid, maintaining a temperature between 0 and 4 degrees Celsius. Fish, aquatic plants, bacteria, and all other lake-dwelling organisms can continue living in this liquid water throughout the winter. Without this protection, many would die. If ice behaved normally, if it sank when it formed, the consequences would be catastrophic. Ice forming on the surface would sink to the bottom. More ice would form at the surface and sink again. This process would continue until the entire lake or ocean froze solid from the bottom up. There would be no insulating layer protecting the liquid water. In winter, many bodies of water would freeze completely. Only the deepest oceans might retain some liquid water at their depths. Even worse, once ice sank to the bottom, it would be insulated from the warm air of summer by the water above it. It would melt very slowly or not at all. Over successive winters, more ice would accumulate on the bottom. Eventually, much of Earth's water would be locked up as bottom ice that never melts. The oceans would gradually freeze, Earth would enter a permanent global glaciation, and the climate would become far more extreme. Life, which depends on liquid water, would be severely constrained or perhaps impossible. This scenario nearly happened anyway, at least twice in Earth's history. Between about 720 and 635 million years ago, during a period called Cryogenian, Earth experienced severe ice ages that may have covered most or all of the planet's surface with ice, an event known as Snowball Earth. Glacial ice extended from the poles to the equator. But even during these extreme glaciations, the fact that ice floats meant that liquid water likely persisted beneath the ice, particularly in the deep ocean. This liquid water provided refuge for life. When volcanic carbon dioxide eventually accumulated in the atmosphere and warmed the planet enough to melt the ice, life survived and eventually flourished. The floating of ice also plays a critical role in seasonal cycles in temperate and polar regions. Every autumn, as temperatures drop, ice begins to form on the surface of lakes and ponds. The ice layer grows thicker as winter progresses, sometimes reaching a meter or more in depth in very cold climates. But beneath this ice, liquid water remains. Frogs burrow into mud at the bottom and enter a state of dormancy. Fish reduce their metabolism and move slowly through the cold but liquid water. Aquatic plants die back but leave seeds or root systems that will regrow in spring. Bacteria and other microorganisms continue their processes, though at reduced rates. When spring arrives and temperatures rise, the ice melts from the top down. The sun warms the ice surface, and meltwater trickles down into the lake, releasing the trapped ecosystem back to active life. If ice sank instead of floating, this seasonal cycle would be impossible. Lakes would freeze solid in winter, killing most of their inhabitants. Only the smallest, most cold-tolerant organisms might survive by entering dormant states, and the diversity of aquatic life would be drastically reduced. The same principle applies to the ocean, though on a much larger scale. In polar regions, sea ice forms on the ocean surface during winter. This ice floats, creating a barrier between the cold air and the liquid ocean beneath. The ocean below remains liquid, with temperatures hovering just below the freezing point of salt water, which is about minus 1.8 degrees Celsius. Marine life, fish, seals, whales, plankton, krill, continues to thrive in this liquid environment. Some organisms, like Antarctic cod, have evolved antifreeze proteins in their blood that prevent ice crystals from forming in their cells even at temperatures below the normal freezing point. The Antarctic ice shelves, which extend out from the continent as floating platforms hundreds of meters thick, demonstrate this principle on a massive scale. These ice shelves float on the ocean because ice is less dense than water. The ocean beneath these ice shelves, though dark and cold, supports unique ecosystems that would not exist if the ice sank. In the Arctic, sea ice covers much of the Arctic Ocean during winter, providing habitat for polar bears, seals, and other ice-dependent species. All of this is possible only because ice floats. The anomalous density of water near its freezing point also affects how lakes mix and circulate. Water is most dense at about 4 degrees Celsius, not at its freezing point. This means that as surface water cools in autumn, it becomes denser and sinks until it reaches 4 degrees. This causes the lake to turn over, mixing oxygen-rich surface water with the deeper layers. But once the surface water cools below 4 degrees, it becomes less dense again and stays at the surface where it eventually freezes. This ensures that the coldest water and any ice remain at the top, while the densest, for-degree water sinks to the bottom, where it provides a slightly warmer refuge for bottom-dwelling organisms. Without this precise behavior, maximum density at 4 degrees and expansion upon freezing, lakes would not overturn in autumn, oxygen would not reach the depths, and the entire ecology of temperate lakes would be different. The fact that water behaves this way is not arbitrary or accidental. It emerges directly from the molecular structure, the biogeometry of the water molecule, the polarity that creates hydrogen bonds, and the specific way those hydrogen bonds arrange molecules in the ice crystal lattice. This property has been operating for as long as Earth has had liquid water and temperatures cold enough to freeze it. For at least 2.4 billion years since the first major glaciation events, ice has been forming and floating on Earth's oceans and lakes. During the ice ages of the past 2.6 million years, enormous ice sheets covered much of North America and Eurasia, sometimes several kilometers thick. These ice sheets formed from accumulated snow that compressed into ice. They flowed slowly like viscous fluids, carving valleys and reshaping continents. But where these glaciers reached the ocean, the ice calved off as icebergs that floated away, carrying rocks and sediment far from their source. All of this happened because ice is less dense than water. The water in your glass right now possesses this same property. If you freeze it, it will expand and float. The hydrogen bonds that hold your water molecules together in shifting, dynamic networks will lock into the hexagonal crystal structure of ice. The The same physics that governs a single ice cube in your freezer also governs the polar ice caps, the winter ice on lakes, and the preservation of aquatic life through seasonal freezes. This seemingly simple property, ice floats, has shaped climate, protected ecosystems, and made complex life possible for billions of years. You've seen how water's structure allows ice to float and protect life, but now you need to understand another fundamental property: water's ability to dissolve more substances than any other common liquid. This property, which emerges directly from water's polar molecular structure, makes water essential for life, for geological processes, and for the transport of materials throughout Earth's systems. The key to understanding water's dissolving power lies in its polarity. As you learned earlier, the water molecule has a bent shape that creates an uneven distribution of electrical charge. The oxygen end carries a slight negative charge, and the hydrogen ends carry a slight positive charge. This makes water behave like a tiny magnet, with a positive and negative end that can interact with charged particles. When you add table salt, sodium chloride, to water, something remarkable happens at the molecular level. Salt is an ionic compound, meaning it's made of positively charged sodium ions and negatively charged chloride ions held together in a crystal lattice by electrical attraction. In the solid crystal, these ions are locked in fixed positions. But when the salt crystal contacts water, the polar water molecules cluster around the ions at the crystal's surface. The negative oxygen end of water molecules is attracted to the positive sodium ions. The positive hydrogen ends are attracted to the negative chloride ions. These attractions are strong enough to overcome the forces holding the ions in the crystal. Water molecules pull sodium and chloride ions away from the crystal surface and surround them in solution. Each ion becomes wrapped in a shell of water molecules with their charged ends oriented toward the ion, a process called hydration. Once in solution, these hydrated ions are dispersed throughout the water. They don't recombine immediately because each ion remains surrounded by its protective shell of water molecules. The salt has dissolved. It has been broken down from an organized crystal into individual ions distributed through the water. This same process works for many other ionic compounds, including minerals and rocks and soils. Water also dissolves many polar molecules, even if they're not ionic. Sugar sucrose is a good example. Sugar molecules contain multiple oxygen and hydrogen atoms arranged in ways that create partial charges across different regions of molecule. These polar regions can form hydrogen bonds with water molecules. When sugar dissolves, water molecules surround the sugar molecules, forming hydrogen bonds with them and separating them from each other. The sugar molecules disperse through the water, held in solution by their hydrogen bond interactions with the surrounding water molecules. But water doesn't dissolve everything. Oils, fats, and waxes are nonpolar. They don't have regions of positive and negative charge. Because they're nonpolar, they can't form hydrogen bonds or electrostatic interactions with water. When you try to mix oil and water, the oil molecules cluster together and the water molecules cluster together, minimizing contact between them. The water molecules would rather hydrogen bond with each other than interact with nonpolar oil molecules. This is why oil floats on water in discrete droplets rather than dissolving. This selective dissolving, water dissolves polar and ionic substances but not nonpolar ones, is crucial for life. Cell membranes are made primarily of lipids, which are nonpolar and don't dissolve in water. This allows cells to maintain their structure and keep their contents separate from the external environment. But within the cell and in the extracellular fluid, water dissolves countless substances, sugars, amino acids, salts, gases, and transports them where they're needed. Water's dissolving power has been operating on geological timescales since the first ocean formed. When rain falls on rock, the water dissolves minerals. Carbonic acid in rainwater reacts with feldspars and other minerals, breaking them down and releasing ions into solution. Silica dissolves. Calcium, magnesium, sodium, potassium, and iron enter the water as dissolved ions. This process, chemical weathering, has been transporting dissolved materials from land to ocean for billions of years. The ocean itself is a vast solution of dissolved materials. Seawater contains about 35 grams of dissolved salts per kilogram of water. The most abundant ions are sodium and chloride, the components of table salt, but seawater also contains significant amounts of magnesium, sulfate, calcium, potassium, and trace amounts of nearly every naturally occurring element. All of these materials were dissolved from rocks and delivered to the ocean by rivers, or were added directly through underwater volcanic activity. The ocean's salinity has been building for billions of years. Early in Earth's history, the ocean was less salty than it is today. As water cycled through the hydrologic system, evaporating from the ocean, falling as rain, weathering rocks, and returning to the ocean carrying dissolved ions, the concentration of salts gradually increased. The ocean reached its current salinity sometime in the Precambrian and has remained relatively stable since then. It stays stable because the rate at which ions are added to the ocean roughly equals the rate at which they're removed through processes like precipitation of minerals and incorporation into sediments. Rivers and groundwater carry these dissolved materials constantly. Every year, rivers deliver approximately 3.9 billion tons of dissolved salts to the ocean. If there were no removal processes, the ocean would become saltier over time. But various mechanisms remove ions from seawater: precipitation of calcium carbonate to form limestone, incorporation of ions into clay minerals, uptake by marine organisms, and burial in sediments. The balance between input and removal keeps ocean salinity relatively constant. Water's dissolving power is equally crucial inside living organisms. Your blood is mostly water, and that water dissolves and transports an extraordinary variety of substances. Oxygen dissolves in water in your lungs, then travels dissolved in blood plasma and bound to hemoglobin inside red blood cells. Carbon dioxide, a waste product of cellular metabolism, dissolves in blood and travels to your lungs to be exhaled. Glucose, amino acids, hormones, vitamins, minerals, all of these dissolve in water and travel through your bloodstream to cells throughout your body. At the cellular level, water dissolves the ions and molecules that cells need to function. Sodium, potassium, calcium, and chloride ions dissolved in cellular fluid participate in electrical signaling in nerves and muscles. Enzymes, proteins that catalyze biochemical reactions, require a water environment to fold properly and function. The substrates that enzymes act upon are usually dissolved in water. The products of enzymatic reactions dissolve in water and can be transported to where they're needed or excreted as waste. Water also participates directly in many biochemical reactions, not just as a solvent but as a reactant. In photosynthesis, water molecules are split to provide electrons and protons, with oxygen released as a byproduct. In digestion, water molecules are added to chemical bonds to break large molecules like proteins and starches into smaller units, a process called hydrolysis. In cellular respiration, water is produced when electrons combine with oxygen at the end of the electron transport chain. Water is not a passive background medium. It's an active participant in the chemistry of life. The ability of water to dissolve gases is also important. Oxygen from the atmosphere dissolves in ocean water, making it available to fish and other aquatic organisms. Carbon dioxide dissolves in water, where it can be used by aquatic plants for photosynthesis. The amount of gas that can dissolve in water depends on temperature and pressure. Cold water can hold more dissolved gas than warm water, which is why cold ocean water near the poles contains more oxygen than warm tropical water. This dissolving power has one more critical role. It makes water difficult to purify. Because water dissolves so many substances, natural water always contains dissolved materials. Rainwater contains dissolved gases from the atmosphere. Groundwater contains minerals dissolved from soil and rock. River water contains sediment, dissolved minerals, and organic matter. Ocean water contains salts, minerals, and countless other dissolved substances. To obtain pure water requires distillation or advanced filtration to remove all these dissolved materials. Yet it's precisely because water dissolves so many things that it's useful for life and for geological processes. The water in your glass right now is dissolving minerals from the pipes it flowed through, gases from the air it contacted, and anything else it encountered on its journey to you. It's never completely pure. But this impurity is not a flaw, it's a feature. Water's ability to dissolve substances, to transport them, to participate in chemical reactions, and to provide a medium for life's processes all stem from the same source. The polar nature of the water molecule, the slight electrical charges that allow it to interact with ions and polar molecules, and the hydrogen bonds that hold it all together. You've explored water's ability to dissolve substances and transport materials, but now you need to understand another critical property: water's role in regulating Earth's temperature. This function emerges from water's unusually high heat capacity and heat of vaporization, properties that make water the planet's primary thermal buffer. Heat capacity is the amount of energy required to raise the temperature of a substance by 1 degree. Water has one of the highest heat capacities of any common substance. It takes 4,184 joules of energy to raise the temperature of 1 kilogram of water by 1 degree Celsius. This is about 5 times more energy than it takes to heat the same mass of rock by the same amount. The reason, once again, lies in hydrogen bonding. When you add heat energy to water, that energy doesn't immediately increase the speed of the molecules, which is what temperature measures. Instead, much of the energy goes into breaking hydrogen bonds. Water molecules are constantly forming and breaking hydrogen bonds with their neighbors, and it takes energy to break those bonds. Only after enough hydrogen bonds have been disrupted can the molecules move faster and the temperature rise. This means water absorbs a lot of heat before its temperature changes significantly. The reverse is also true. When water cools, it releases energy slowly. As molecules slow down, they form more stable hydrogen bonds, and energy is released in the process. Water resists temperature change in both directions. It warms slowly and cools slowly. This property has profound effects on climate and weather. The ocean, which covers about 71% of Earth's surface and contains 96.5% of all water on the planet, acts as a massive thermal reservoir. During the day, particularly in tropical regions, the ocean absorbs enormous amounts of solar energy. The water warms, but because of its high heat capacity, the temperature rise is modest. At night, the ocean releases this stored energy back to the atmosphere, warming the air above it. This moderates temperature swings between day and night in coastal regions. The same principle operates on seasonal timescales. During summer, the ocean absorbs heat and warms gradually. During winter, it releases that stored heat and cools gradually. Coastal regions experience much smaller temperature differences between summer and winter than continental interiors do. San Francisco, surrounded by ocean on 3 sides, rarely sees temperatures below freezing or above 30 degrees Celsius. Kansas City, in the center of the continent, experiences winter lows below -20 degrees Celsius and summer highs above 38 degrees Celsius. The difference is water's moderating influence. Ocean currents distribute this heat globally. Warm water from the tropics flows toward the poles, carrying thermal energy with it. Cold water from polar regions flows toward the equator, where it absorbs heat. The Gulf Stream, a warm current flowing from the Gulf of Mexico across the Atlantic toward Europe, carries about 100 times more heat than all human energy consumption combined. This heat warms Western Europe, making it significantly warmer than regions at similar latitudes in North America. London is at about the same latitude as Calgary, but London rarely experiences Calgary's harsh winters because the Gulf Stream moderates its climate. Water's high heat of vaporization adds another layer of climate regulation. Heat of vaporization is the energy required to convert liquid water to vapor without changing temperature. For water, this value is about 2.5 million joules per kilogram, one of the highest of any substance. When water evaporates, it absorbs this energy from its surroundings, cooling them. When vapor condenses back into liquid, it releases this energy, warming its surroundings. This creates a massive heat transport system. Water evaporates from the warm tropical oceans, absorbing heat. The vapor rises into the atmosphere and is carried by winds toward cooler regions. When the vapor condenses into clouds and eventually falls as rain, the stored heat is released, warming the atmosphere at higher latitudes or elevations. This atmospheric heat transport, driven by evaporation and condensation, moves about 40% of all heat that flows from equator to poles. You can feel this effect directly through evaporative cooling. When you sweat, water from your skin evaporates. The evaporation requires energy, which it takes from your skin, cooling you down. Dogs pant, using evaporation from their tongues and respiratory passages to cool themselves. Plants transpire water from their leaves, which cools the leaves and prevents overheating in intense sunlight. All of these cooling mechanisms rely on water's high heat of vaporization. On geological timescales, water has regulated Earth's climate for billions of years. Early in Earth's history, when the sun was about 30% dimmer than today, the planet should have frozen solid. But it didn't, partly because greenhouse gases like carbon dioxide and methane kept temperatures warm, but also because the ocean absorbed and stored solar energy, moderating temperature extremes. As the sun gradually brightened over billions of years, chemical weathering, which requires liquid water, removed carbon dioxide from the atmosphere and stored it in carbonate rocks, preventing runaway warming. Water participated in this feedback loop, helping keep Earth's surface temperature within a range suitable for liquid water and life. Water's role as Earth's thermostat has been particularly important during times of climate stress. During the ice ages of the past 2.6 million years, when continental ice sheets advanced and retreated multiple times, the ocean buffered temperature changes and prevented more extreme swings. During the warm periods between ice ages, the ocean absorbed excess heat and moderated warming. This buffering continues today. The ocean has absorbed about 90% of the excess heat from human-caused greenhouse gas emissions over the past 50 years, slowing the rate of atmospheric warming but also warming the ocean itself. Water vapor in the atmosphere also acts as a greenhouse gas, though its behavior is complex. Unlike carbon dioxide, which persists in the atmosphere for decades to centuries, water vapor cycles through in about 9 days. The amount of water vapor the atmosphere can hold depends strongly on temperature. Warmer air holds more vapor. This creates a feedback loop. Warming increases evaporation, which adds more water vapor to the atmosphere, which enhances the greenhouse effect, which causes more warming. But more water vapor also means more clouds, and clouds have complex effects on temperature. They reflect incoming sunlight, cooling the surface, but they also trap outgoing heat, warming it. The net effect depends on cloud type, altitude, and coverage. Despite these complexities, water's overall effect has been to stabilize Earth's climate within a range where liquid water can exist. For nearly 4 billion years, through dramatic changes in solar brightness, atmospheric composition, and continental configuration, Earth has maintained liquid oceans. Water's thermal properties, its high heat capacity, and heat of vaporization have been essential to this stability. Without water acting as a thermal buffer, Earth's temperature would swing wildly between day and night, between summer and winter, and between different climate states. The planet might have become as frozen as Mars or as hot as Venus. Instead, water has kept Earth habitable. The water in your glass carries these same thermal properties. It takes more energy to heat than almost any other substance. It releases that energy slowly when it cools. If you were to freeze it, the phase change would release heat. If you were to boil it, the phase change would absorb tremendous amounts of heat. These properties, which emerge from hydrogen bonding and molecular structure, operate identically whether in your glass, in the ocean, or in a cloud forming above you. Water regulates temperature at every scale, from the climate of the planet to the interior of your cells. You've followed water through geological cycles and watched it regulate climate, but now you need to look closer, down to the microscopic level where life actually happens. Water is not just the environment in which life exists. It is the medium that makes life possible at the most fundamental level. Every cell in every organism is filled with water, and that water actively participates in the chemistry of life. A typical cell is about 70 to 80% water by mass. This water is not passive filler material. It's an active participant in virtually every cellular process. The water molecules inside your cells are constantly forming and breaking hydrogen bonds with each other, and with the thousands of different molecules dissolved in the cellular fluid. These interactions determine how molecules fold, how they move, and how they react with each other. Proteins, the workhorses of cellular function, depend entirely on water for their structure and activity. A protein is a long chain of amino acids that must fold into a specific three-dimensional shape to function. The way this chain folds is determined largely by how its amino acids interact with water. Some amino acids are hydrophilic. They have polar or charged groups that form hydrogen bonds with water. Other amino acids are hydrophobic. They have nonpolar groups that avoid water. When a protein folds in water, the hydrophobic amino acids cluster together in the interior of the protein, away from water. The hydrophilic amino acids arrange themselves on the outside, in contact with the surrounding water. This arrangement is called the hydrophobic effect, and it drives the folding of almost all proteins. Without water, proteins would not fold correctly. Without correct folding, they cannot function. The three-dimensional structure of every enzyme, every structural protein, every molecular machine in your cells exists because of how amino acids interact with water. Enzymes, proteins that catalyze biochemical reactions, require water to function. Many enzymes use water molecules directly in their catalytic mechanisms. In hydrolysis reactions, enzymes break chemical bonds by adding water molecules. During digestion, enzymes break down proteins, carbohydrates, and fats by inserting water molecules into the bonds holding these large molecules together. When you eat a protein, enzymes in your stomach and intestines add water to the peptide bonds connecting amino acids, splitting the protein into its component parts. When you eat starch, enzymes add water to the bonds connecting glucose molecules, releasing individual sugars that your cells can use. Water also participates in condensation reactions, where two molecules join together and release a water molecule. When your cells build proteins from amino acids, they connect the amino acids and release water. When cells synthesize DNA or RNA, they join nucleotides together and release water with each bond formed. Water is both a reactant and a product in countless cellular reactions, not just a spectral medium where reactions happen. The chemistry inside cells happens in an aqueous environment, a water solution containing thousands of different dissolved substances. Ions like sodium, potassium, calcium, chloride, and phosphate are dissolved in cellular water. These ions are essential for electrical signaling, enzyme function, pH regulation, and maintaining osmotic balance. Small organic molecules, glucose, amino acids, nucleotides, vitamins, are dissolved in water and transported to where they're needed. Larger molecules like proteins and nucleic acids are suspended in water. Their surface is covered with a hydration shell of water molecules. Cell membranes, which separate the cell interior from the external environment, owe their structure to water. Membranes are made primarily of phospholipids, molecules with a hydrophilic head and two hydrophobic tails. In water, these molecules spontaneously arrange themselves into a double layer with the hydrophobic tails facing inward, away from water, and the hydrophilic heads facing outward, in contact with water on both sides. This bilayer structure forms automatically because of how phospholipids interact with water. Every membrane in your body, around every cell, around every organelle, exists because lipids avoid water and organize themselves to minimize contact with it. Water moves across membranes through specialized channels called aquaporins. These protein channels allow water molecules to flow through the membrane while preventing ions and other molecules from passing. Your cells constantly regulate their water content, using aquaporins to allow water in or out depending on osmotic conditions. When the concentration of dissolved substances is higher inside a cell than outside, water flows in through aquaporins to dilute the internal contents. When the concentration is higher outside, water flows out. This osmotic balance is critical for maintaining cell volume and preventing cells from swelling and bursting or shrinking and shriveling. Photosynthesis, the process that produces oxygen and organic compounds from sunlight, uses water as a raw material. In the light reactions of photosynthesis, chlorophyll absorbs light energy and uses it to split water molecules. Each water molecule is broken into hydrogen and oxygen. The hydrogen is used to create energy-carrying molecules and eventually to build sugars. The oxygen is released as a byproduct. It's the oxygen you breathe. Every breath you take contains oxygen that was once part of a water molecule inside a plant or algae cell. Cellular respiration, the process that extracts energy from food, produces water as a final product. In the electron transport chain, the final stage of respiration, electrons and protons combine with oxygen to form water. Every time your cells burn glucose for energy, they produce carbon dioxide and water. The water created by respiration becomes part of the cellular water, indistinguishable from water that entered the cell from outside. Your cells both use water and create water as part of their normal metabolism. Water's properties allow cells to maintain their internal organization against the randomizing effect of heat. The cell interior is crowded with proteins, nucleic acids, membranes, and other structures. These structures must maintain specific arrangements to function properly. Water provides the medium that allows molecules to move and find each other, while also stabilizing their structures through hydrogen bonding. If cells contained a different liquid, one without water's unique properties, the molecular machinery of life could not operate. DNA and RNA, which store and transmit genetic information, depend on water for their structure. The famous double helix of DNA is stabilized partly by hydrogen bonds between the base pairs in the center of the molecule. But the overall structure also depends on how the DNA molecule interacts with surrounding water. The sugar-phosphate backbone on the outside of the helix is hydrophilic and forms hydrogen bonds with water. The bases in the interior are relatively hydrophobic and are shielded from water by the structure of the helix. This arrangement is stable in water, but would collapse in a different solvent. The same water that fills your cells has been cycling through living organisms for billions of years. Water molecules absorbed by a plant may become part of glucose during photosynthesis. When an animal eats the plant, those molecules may be released during digestion or respiration. The animal may excrete water through urine or sweat. That water re-enters the environment, evaporates, falls as rain, and eventually enters another organism. The same water has passed through countless cells, participated in countless reactions, and will continue doing so as long as life exists. Your own body demonstrates water's cellular importance. Roughly 60% of your body mass is water. Your brain is about 75% water. Your blood is about 90% water. Every cell contains water. Every tissue is saturated with it. When you're dehydrated, even by a few percent, your cells cannot function optimally. Proteins don't fold correctly, reactions slow down, and cellular processes become impaired. Water is not an optional component of cellular life. It's the essential foundation. You now follow water as it moves through your own life, tracing its journey from the landscape to your glass and through your body. Each step is essential, not just for human survival, but for the interconnected balance of life itself. The water you drink today links you directly to ancient rains and rivers, the weathered stones of distant mountains, and the cycling of oceans and clouds. First, consider the path drinking water takes. Rain falls on the earth, soaking into soil or running across ground as rivers and streams. Some seeps into underground aquifers, reservoirs of water stored in porous rock and soil, sometimes for decades or even centuries before emerging again as springs or wells. Eventually, this water is collected by municipal utilities, wells, or direct collection from rivers and lakes and delivered to treatment facilities. Here, it's filtered and purified, often through several stages to remove suspended solids, bacteria, and dissolved substances, making it safe to drink. In many modern systems, tiny traces of minerals help provide essential nutrients and the familiar taste associated with clean, potable water. Once inside your body, water begins its vital work. serving as the foundation of every cell, tissue, and organ. About 60 of an adult's body weight is water. It forms the basis of your blood, bathes every cell, cushions your brain and spinal cord, lubricates your joints, and helps regulate your internal temperature through sweat and exhaled moisture. Every movement, every heartbeat, and every thought relies on water circulating nutrients and removing waste. Your bloodstream is more than 90 water, carrying dissolved oxygen from your lungs to tissues and delivering nutrients from the food you eat to every cell. As you breathe, the water in your lungs helps maintain delicate mucous membranes and aids in the exchange of gases. Water lubricates joints and eyes, protects organs from shocks, and keeps your skin supple. In the digestive system, it dissolves food, allowing nutrients to be absorbed into your bloodstream. Your kidneys filter your blood relentlessly, extracting waste dissolved in water and creating urine for excretion, an ongoing cleaning cycle that relies entirely on an adequate supply of water. Without enough water, the effects are immediate and fundamental. Even mild dehydration can impair brain function, reduce energy and physical capacity, and disrupt essential processes at the cellular level. Severe dehydration quickly becomes dangerous, affecting the brain, heart, muscles, and kidneys. This highlights an ancient fact. Water is not simply something you consume. It is a deeply active, ever-circulating component of your living self. As you reach for a glass of water, you complete a cycle that starts with Earth's deep geological past and runs through clouds, rivers, soils, treatment plants, and ultimately your own cells. That water is older than humanity, and after leaving your body, will continue its journey, carrying minerals, shaping landscapes, and sustaining new life again and again. You've followed water through oceans and atmospheres, through rivers and cells, and now you arrive at a profound realization. You are not simply a body that contains water. You are made of water. Roughly 60% of your adult body weight is water, and this percentage has defined you since before you were born. When you were an infant, you were about 75% water. As you age, that percentage decreases slightly, but it will never drop below about 45%, even in old age. Water is not something you contain. It is something you are made from. Consider what this means at the level of tissues and organs. Your brain is about 73 to 80% water. Every thought you have, every memory you form, every emotion you feel occurs in a structure that is mostly water. Your heart, which beats approximately 100,000 times per day, pumping blood through your body, is also 73 to 75% water. Your lungs, which extract oxygen from air and expel carbon dioxide, are about 83% water. Your muscles, which allow every movement from blinking to running, are 70 to 75% water. Even your bones, which seem solid and permanent, are about 22 to 31% water. Your blood is approximately 50 to 83% water, depending on how you measure it. Plasma, the liquid component of blood, is about 90% water. This water carries dissolved oxygen from your lungs to every cell in your body. It transports glucose, amino acids, hormones, vitamins, and minerals to wherever they're needed. It carries waste products, carbon dioxide, urea, and other metabolic byproducts to your lungs, kidneys, and liver for elimination. Without this water-based transport system, your cells would be isolated, unable to receive nutrients or expel wastes, and would quickly die. The water in your body exists in two main compartments. About 2/3 of your body water is intracellular water, water inside your cells. This water fills the cytoplasm, where most of the cell's metabolic reactions occur. It dissolves enzymes, substrates, and products, allowing biochemical reactions to proceed. It provides the medium in which proteins fold, DNA replicates, and organelles function. Without this intracellular water, the molecular machinery of life could not operate. The remaining 1/3 of your body water is extracellular water, water outside your cells. This includes the water in your blood plasma, the interstitial fluid that bathes your cells, and the specialized fluids in places like your joints, eyes, and digestive system. Extracellular water transports oxygen, nutrients, and signaling molecules to cells, and carries away carbon dioxide and metabolic wastes. It provides cushioning and lubrication, the synovial fluid in your joints, the cerebrospinal fluid protecting your brain and spinal cord, the aqueous humor in your eyes. All of these are water-based solutions with dissolved proteins, salts, and other molecules. Your body constantly regulates its water content with remarkable precision. Your kidneys filter about 180 liters of blood per day, removing waste products and excess water while retaining essential substances. Most of this filtered fluid is reabsorbed. Your kidneys produce only about 1 to 2 liters of urine per day under normal conditions. When you're dehydrated, your kidneys conserve water by producing concentrated urine. When you've consumed excess water, they produce dilute urine to eliminate the surplus. This regulation is controlled by hormones that sense your blood's concentration of dissolved substances and adjust kidney function accordingly. You also lose water through other routes. You exhale water vapor with every breath. The warm, moist air from your lungs carries away water that evaporates from the surfaces of your airways and alveoli. You lose water through your skin, both through sweating and through insensible water loss, the constant, barely noticeable evaporation that occurs even when you're not sweating. In hot weather or during exercise, you can lose several liters of water per hour through sweat. This evaporative cooling prevents your body from overheating, but requires constant water replacement. The water you lose must be replaced. You obtain water primarily by drinking fluids and eating foods that contain water. Fruits and vegetables can be 80 to 95% water. Your body also produces a small amount of metabolic water, water created as a byproduct of cellular respiration when nutrients are burned for energy. For every 100 grams of fat your cells metabolize, they produce about 107 grams of water. For carbohydrates and proteins, the yield is lower but still significant. This metabolic water provides perhaps 250 to 350 milliliters per day, a small but meaningful contribution to your water balance. The regulation of your body's water content is remarkably sophisticated. When you become even slightly dehydrated, specialized sensors called osmoreceptors in your hypothalamus detect the increase in blood concentration. These osmoreceptors trigger two responses. First, they stimulate the sensation of thirst, motivating you to drink. Second, they signal the pituitary gland to release antidiuretic hormone, also called vasopressin, into your bloodstream. Vasopressin travels to your kidneys, where it binds to receptors on cells in the collecting ducts, the final portion of the kidney tubules where urine is concentrated. This binding triggers a cascade of events inside these cells. Tiny water channels called aquaporin-2 proteins, which are normally stored in vesicles inside the cells, move to the cell membrane and insert themselves there. These aquaporin channels create pores that allow water to flow from the urine back into the bloodstream. More water is reabsorbed, less urine is produced, and your body conserves water. When you're well hydrated or have consumed excess water, the opposite happens. Your blood becomes more dilute. Osmoreceptors detect the lower concentration and vasopressin secretion decreases. Without vasopressin, the aquaporin-2 channels are removed from the cell membranes and stored again in vesicles. Water cannot pass through the collecting duct walls as easily, so less water is reabsorbed and more is excreted as dilute urine. This system can adjust urine concentration over a wide range, from very concentrated when you're dehydrated to very dilute when you're overhydrated. The water molecules that make up your body right now are temporary residents. Water cycles through you constantly. The water you drink enters your stomach and intestines, is absorbed into your bloodstream, circulates through your body, enters and leaves cells, participates in countless biochemical reactions, and is eventually excreted through urine, sweat, breath, or feces. The average residence time of water in a human body is about 9 to 10 days, meaning that in a week and a half, most of the water molecules currently in your body will have been replaced by new ones. But the water that leaves your body doesn't disappear. The water you excrete as urine flows into sewage systems or septic tanks, is treated, and eventually returns to rivers or aquifers. The water you exhale as vapor enters the atmosphere, where it may condense into clouds and fall as rain. The water you lose as sweat evaporates into the air. All of this water re-enters the water cycle, moving through the same processes that have been operating for billions of years. This means that the water molecules in your body right now are ancient. They are the same molecules that have been cycling through Earth's system since the ocean first formed nearly 4 billion years ago. Some of those molecules may have once been part of a dinosaur, or a tree in a primordial forest, or a drop of rain that fell on the first continents. They have passed through countless organisms, evaporated from countless oceans, and fallen as rain on landscapes that no longer exist. And after they leave your body, they will continue that journey, entering new organisms, shaping new landscapes, participating in new processes. You are not separate from the water cycle. You are part of it. Your body is a temporary vessel through which water flows, a brief pause in the endless circulation of H2O molecules across the planet. Every breath you take, every heartbeat, every thought requires water that came from somewhere else and will go somewhere else when you're done with it. You are made of water, sustained by water, and ultimately, you will return your water to the cycle that birthed you. You return now to where this journey began, to the present moment, to the glass of water in your hand. But everything has changed in your understanding. This water is no longer just a simple liquid you drink to quench thirst. It is the culmination of a story that spans 4.5 billion years, connecting you to the formation of planets, the cooling of a molten Earth, and the emergence of life itself. The water molecules in your glass are ancient beyond measure. They condensed from the first rains that fell on the cooling crust of the early Earth. They filled the primordial ocean when the planet was young and hot. They have cycled through countless organisms, evaporated from vanished seas, and fallen as rain on landscapes that existed before complex life appeared. These same molecules have been part of dinosaurs and ancient forests, of glaciers and rivers, of clouds and morning dew. Each molecule retains its identity. 2 hydrogen atoms bonded to 1 oxygen atom at an angle of 104.5 degrees. This bend geometry creates the polarity that gives water all its remarkable properties. The hydrogen bonds that form between molecules allow water to exist as a liquid on Earth's surface, to dissolve more substances than any other common solvent, to moderate climate through its high heat capacity, and to expand when it freezes so that ice floats and protects life beneath. None of this is accidental. All of water's life-sustaining properties emerge from this simple molecular architecture. The water you hold has traveled vast distances to reach you. It may have evaporated from the Pacific Ocean, risen into the atmosphere, condensed into clouds, and fallen as rain in mountains hundreds of miles away. It flowed through soil and rock, dissolved minerals along the way, joined streams and rivers, and was collected, treated, and delivered through infrastructure built by human civilization. Yet for all this modern intervention, the water follows the same physical principles that have governed its movement for billions of years. As you drink, this water becomes part of you. Within minutes, it will be absorbed through your intestinal walls and into your bloodstream. Your kidneys will begin processing it, your cells will use it for countless biochemical reactions, and you will incorporate it into the 60% of your body weight that is water. The water molecules will join the intracellular fluid that fills your cells and the extracellular fluid that bathes them. They will help transport oxygen and nutrients, remove waste products, regulate your temperature, and participate in the molecular machinery that keeps you alive. But your ownership of these molecules is temporary. Within days or weeks, they will leave your body through urine, sweat, or exhaled breath. They will rejoin the water cycle, moving through sewage treatment plants or evaporating into the atmosphere. They will become part of new clouds, fall as new rain, nourish new plants, sustain new organisms. The cycle that brought them to you will continue, as it has for nearly 4 billion years. This continuity is perhaps the most profound aspect of water's story. While mountains rise and erode, while species evolve and go extinct, while continents drift and climates change, water endures. The same molecules that witnessed the birth of life continue to sustain it. The ocean that covered the early Earth still covers 71% of the planet's surface. The water cycle that began when the first drops condensed from the cooling atmosphere still redistributes heat, carves landscapes, and connects all living things. In your glass, you hold a sample of Earth's memory. These molecules carry within their wanderings the history of the planet, the story of cooling magma and forming oceans, of emerging continents and evolving life, of ice ages and warm periods, of the first microbes and the first forests, of dinosaurs and human civilization. They are witnesses to everything that has happened since Earth became a water world. Yet water's story is not finished. These molecules will continue their journey long after you are gone. They will see landscapes you cannot imagine, sustain organisms not yet evolved, experience climate changes yet to come. The water cycle will continue, carrying Earth's waters through their endless circulation between ocean, atmosphere, land, and life. Water will remain, as it has been from the beginning, the foundation of everything that lives. This is the end of your journey. The water in your glass connects you to the deepest history of Earth and to the farthest future it will know. When you drink, you participate in a process that is both utterly ordinary and cosmically significant. You join your brief existence to the timeless circulation of molecules that have sustained every living thing, shaped every landscape, and will continue long after all present life is past. In this simple act, raising water to your lips, you complete a circle that began with the formation of planets and will continue until the Earth itself is no more. Rest now, knowing that you are part of this ancient flow, this endless cycle, this quiet miracle of H2O that makes all life possible.